In this video, we're going to see how we can use the simplex method for solving minimization problems. And we can use the same steps that we use for the maximization problem with some slight adaptation. Now we're looking at a standard minimization problem. That's where the objective function is to be minimized, all variables are non-negative, and all the linear constraints have greater than or equal to in the statement. So to solve this problem, we're going to convert the minimization problem to a maximization problem. Right? The minimization problem, the original problem, is referred to as the primal problem, and the maximization problem that we're converting it into is referred to as the dual problem. All right, so looking at the steps for solving this minimization problem. First, write the tableau for the primal problem. Or tableau, just fancy word for table, right? You're writing out a table for your x values, y values, and the constants on the right-hand side. Okay, then you're going to interchange. You're going to switch the columns and rows. The columns will become your rows will become your columns. And instead of calling your variables x and y, call them u and v. And then you will proceed the same way that you did with the maximization problems, except that your slack variables will now be x and y. Then you'll solve the maximization problem, the dual maximization problem, using the same steps that we used in the previous videos. But then the optimal solution, instead of being the numbers on the last column, the optimal solution will be in the bottom row. The x and y values in the bottom row will be your optimal solution. So let's see how this works using an example. Okay, in this example, we want to minimize the cost function, c equal 4x plus 2y, subject to the following constraints: 5x plus y greater than or equal to 5, 5x plus 3y greater than or equal to 10, and our typical constraints, x and y both have to be greater than or equal to 0. Okay, so starting this out, write this out as just as a table. Okay, listing out your x values, your y values, and that right-hand side, your constant. All right, so your constraints, you got the 5x plus 1y greater than or equal to 5. So 5, 1, 5, and then 5x plus 3y greater than or equal to 10. And also list out your objective function, 4x plus 2y equal to a constant of 0. Okay, so now we're going to interchange the rows and the columns. And we're going to call our variables u and v now instead of x and y. Okay, so we're going to write 5, 5, 4 as our first row. 1, 3, 2 becomes our second row. And 5, 10, 0 becomes our third row. Okay, so this is now our dual problem. We can think of this as maximizing the profit function 5, 5u plus 10v subject to 5u plus 5v less than or equal to 4, u plus 3v less than or equal to 2. All right, so we have converted a minimization problem to this maximization problem. Now that we've done that, we can proceed with the same steps as we've seen in the previous videos. So where we can set this up by introducing slack variables to force equality. Our slack variables will be x and y. Then u plus 3v plus y equal to, and then for the objective function, subtract 5u and subtract 10v from both sides. That gives us a negative 5u minus 10v plus p equals 0. And that becomes the matrix 5, 5, 1, 0, 0, 4, 1, 3, 0, 1, 0, 2, negative 5, negative 10, 0, 0, 1, 0. Okay, so we'll start with the largest non-negative entry in that last row. Take the ratios 4 divided by 5 and 2 divided by 3. Now, 4/5 is 0.8, 2/3 is about 0.67 rounded. So we're taking the smaller of those two ratios, which is the 2/3. So we're going to use this as our pivot. So we want that 3 to become a 1. We'll do that by multiplying by 1/3. That's 1/3, 1, 0, 1/3, 0, 2/3. Everything else stays the same. Now that we've got the 1 in place, we want everything else in that column to be zeros. So we can do that by taking row 1 minus 5 times row 2, and row 3 plus 10 times row 2. Row 2 will remain the same. Okay, so row 1 minus 5 times row 2. Let's see what that's going to be. So here's row 1. And here is negative 5 times row 2. Negative 5/3, negative 5, 0, negative 5/3, 0, and negative 10/3. Which is 10/3, 0, 1, negative 5/3, 0, and 2/3. And then for the row 3 plus 10 times row 2, we have 10/3, 10, 0, 10/3, 0, and 20/3. That's negative 5/3, 0, 0, 10/3, 1, and 20/3. Okay, so now we still have a negative in that last row. And we need to see which one that we're going to pivot around. And what I mentioned earlier in an earlier video, right, since we've already used this as our 1, this one's not going to be 1 also. It's going to be the alternating entry. And you can verify that using the ratios. All right, so we want this 10/3 to become a 1. We can do that by multiplying by 3/10. That's 1, 0, 3/10. Negative 1/2, 0, and 1/5. Everything else stays the same. right, so now we want the 1/3 and the -5/3 to become 0. That can be accomplished by taking row 2 minus 1/3 times row 1, and row 3 plus 5/3 times row 1. All right, so row 2 minus 1/3 row 1. So row 2 is 1/3, 1, 0, 1/3, 0, 2/3. And negative 1/3 times row 1 is negative 1/3, 0, negative 1/10, 1/6, 0, and negative 1/15. So this becomes 0, 1, negative 1/10, 1/3 over 1/6 would be, see, that's 2/6 plus 1/6, that's 3/6, which is 1/2, 0, and 9/15, which can be reduced down to 3/5. And then row 3 plus 5/3 row 1. So here's row 3. And 5/3 times row 1. 5/3, 0, 1/2. 5/3 times negative 1/2 is negative 5/6, 0, and 5/3 times 1/5 is 1/3. All right, so that's 0, 0, 1/2, 15/6, which is 5/3, 1, and 21/3, which is 7. Go back and make one slight correction. 15/6 should be 5/2. All right, so now that we've got all positive numbers in the last row, that means we're finished. And when we had a maximization problem, right, this last column gave us our solution, right, 1/5 and 3/5. All right, but this is the dual problem. So instead of looking at the last column, we're looking at the bottom row. All right, so this 1/2, 5/2, remember this is u, v, x, y. All right, so this 1/2, 5/2 is our optimal solution, which gives us a minimum cost of 7.